topic for today's somewhat short video is going to be an introduction to trends in periodicity. So specifically what we want to talk about here, or look at, are trends in the periodic table of various properties that depend upon electron configuration. Okay, so we know how to do electron configurations now, so we should be able to talk about these various trends within the periodic table. Well, let's focus on what these properties are that we want to talk about. So our first property is going to be essentially one that describes the size of the atom. So for us, this is going to be a measurement of what we call covalent radius. All right? So as I mentioned, it's a measurement of atomic size. So the idea here is that when we talk about a covalent radius, what we're really talking about is two identical atoms covalently bonded together. Now in this case, we could have a fluorine atom bonding with another fluorine atom by way of sharing electrons. Now when we do this, what we can make a measurement of is the distance between the two nuclei. So if this is one fluorine atom here and this is the neighboring fluorine atom here, we should be able to measure an internuclear distance. All right, in this particular case, that internuclear distance is going to be 128 picometers. Now, if we want to get an estimate of the radius of an individual atom, what we're going to do is we're going to take that internuclear distance and we're going to divide it by 2. Okay, so in other words, that's kind of like taking a line and just breaking it right down the center here and saying that half of the atom, or rather half of the molecule is this, the other half is over here. So if we take half of that, that ought to be about the radius of a single atom of fluorine. Okay, so we take our 128 picometers, we divide by 2, and we get an atomic radius of 64 picometers. Okay, so essentially we're just going to refer to this as an atomic radius. So it tells us something about the physical size of the atom. All right, so that's our first property. All right, so the second property that we'd like to talk about here is the first ionization energy or potential. Now what this is the energy required to extract 1 mole of electrons from 1 mole of atoms of a given element in the gaseous phase. So a good example of this might be the reaction that corresponds to the first ionization energy of sodium. So what we're starting out here, if we just look at this on an atom for atom basis here, is that we're looking at an individual sodium atom here. All right, it's in gas phase, and what I want to do is extract an electron away from it. So what that means is I have to put some energy into that atom to take that electron and yank it out. Now typically that electron is going to be one of the outermost valence electrons because those would be the easiest ones to extract from an energy perspective. All right? So generally speaking, since we're doing this per mole of atoms, okay, so it's 1 mole of these things that we're actually ionizing here, we're having to put energy in. So this is typically going to be an endothermic process. I have to put energy into the atom to be able to extract that mole of electrons. All right? So in the case of sodium, that turns out to be a value of 490 kilojoules per mole of sodium atoms that I extract 1 mole of electrons from. Okay, so an endothermic value there. Makes sense when you think about it because that electron is actually stable inside of the atom. So it requires energy to come in and rip it out. All right, so that's another property that we can follow with regard to periodic trends. Now the last property we want to talk about is something called electron affinity. And electron affinity is just the opposite process of first ionization potential. So this is going to be the energy change associated with adding 1 mole of electrons to 1 mole of neutral atoms of a given element in the gas phase. We can demonstrate this with a reaction of fluorine atom. So what I've got here is an isolated fluorine atom in the gaseous phase, and what we're going to do is we're going to shove an extra electron into it. All right? So when we put that electron in, what we're going to get is a fluoride ion in the gas phase with a 1- charge, because again, I've picked up an extra electron here. Now, if I do that across 1 mole of electrons and 1 mole of fluorine atoms, it turns out that that value from an energetics point of view is minus 322 kilojoules per mole. So what we notice here is that it's an exothermic value. All right? So mainly when we look at these things, they're going to tend to be, but not always, exothermic. And that kind of sort of makes sense because we're putting an extra electron into a neutral atom. So it's generally going to be a fairly low-lying energy-wise orbital for me to stick that electron into. So I should actually get energy back when I do that. However, as we're going to see, there are some individual cases where that's not the situation. All right? So with these three different properties in mind, our goal now, come class time, is to see how these properties are actually going to trend in the periodic table for various main group elements. We're going to leave the transition metals out for now, as we do one of two things. As first, we move across a row of the periodic table. We're going to see how each one of these properties is going to vary. Is it going to increase, decrease, or stay the same? And then we're going to do the very same thing as we move down a column or a group in the periodic table. Again, we want to take a look and see whether each one of these properties will increase, decrease, or stay the same. Okay, so keep in mind, our goal for class next time is to look at how these various trends actually move in the periodic table as we do those things. So we'll see you then.